we're going to use what's known as the method of initial rates. Let's say we have this reaction. A moles of A react with B moles of B to form C moles of C. So we would write the rate, and that's literally a rate, something in comparison to time. That's what a rate is, and in this case it's usually concentration, or it could be pressures for an entirely gas reaction, is equal to a constant that we denote with a K times the concentration of the reactant A raised to some power, and it's not always the coefficient, times the other reactant, the concentration, that's what the brackets mean, raised to some power. And again, it may or may not be that concentration. So A and B recognize the concentrations at some point in time, and the K is a constant that's unique to that particular reaction, that particular temperature, and so we have units for K that could vary depending on what the exponent value is for M and N. So that's what we refer to as the order of reaction, the M and N exponents, or how we define what's called order of reactions. And we must determine that experimentally. So in order to do that, you need some data. And the data would look something like you see in this table. The method of initial rates is how we find and write the rate law with values for the different parts, like the exponents for those concentrations and the constant value that you need to relate them. So the first thing we do is solve for those exponents. I don't know why they're called M and N instead of A or B or whatever, but they're called M and N normally, and we can look at a series of initial concentrations. The initial concentration in this reaction is for the reaction of ammonia with the nitrite ion. And so what we do is we start, first we're going to have 0.01 molar ammonium ion and 0.2 molar nitrite ion. Then we're going to do a complete experiment, let that run, and we're going to say that we see the molarity per second, the change in molarity, moles per liter per second, as 5.4 times 10 to the negative second. And so we just keep running 6 different experiments where we keep changing one concentration or the other, and we organize it in a table. Then we need to pick 2 to compare to each other. So we're going to choose 2 trials that have one concentration in common. 2 trials have one concentration in common. Set up a ratio between those. So you see I've written rate 3 over rate 1, so I'm going to pick experiment number 3, and it's bigger, so I put it on top. You can put 1 over 3. I just like to have whole numbers instead of decimal numbers, and divide it by rate number 1. Now remember, the rate is the rate of the reaction. That's that observed initial rate over there in that column, the third column. And then we're going to say equals the constant times the initial concentration, which is given in the table for number 3 is 0.04 raised to some power m, times the concentration for number 3 for the nitrite is 0.2 raised to some power n, and the initial rate was 21.5 times 10 to the negative 7. Then I'm going to compare it to number 1 because it also has a 0.2 molar nitrite ion. So I'm going to just do the math. K divided by K is 1. Anything divided by itself is 1. 0.4 to the m divided by 0.01 to the m remains. 0.2 to the n divided by 0.2 to the n, well, those are the same. They cancel out. They're equivalent to 1. And 21.5 divided by 5.4, well, that's 4. So I have 0.04 to the m divided by 0.01 to the m is 4. And I can rearrange that and say 0.01 divided by 0.04 divided by 0.01 to the m power is equal to 4 to the m power. And that lets me solve as that coefficient or that exponent is going to be 1. And I can repeat this with a comparison, and now that I know what the exponent is for m, I can pick 2 rates that vary with the other reactant concentration. In this case, I need differing values for the nitrite, and you see I have 0.8 over 0.2, and I have the 2 rates. These are the words rate, that the change in concentration per unit time, and I can do the math again, and I find that n is equal to 1. Now that I know what m and n are, I can write the rate law. And that's just simply the rate law is the word rate equals the constant times the reactant raised to the first power times the other reactant raised to the first power that I just solved for. It says law, if you can't read it. All right, so now that m and n are known, I need to find k. So I can use any trial I want. I know everything. I know that the rate was given from the table in the last column. I'm going to pick trial number 2 here, and so I picked that rate from the second row. I picked this concentration for the nitrite, and it's raised to the first power, and I picked the concentration for the ammonium, it's raised to the first power. My only variable is k. Doing the math, that lets me rearrange and solve for the k, and it also lets me pay attention to my units. For the unit 4, when I have what's known as a second order reaction, because I have 2 different reactants, each raised to the first power, so I add my reactants, that'd be second order. That gives me my unit as 1 per molarity per second, or liters per mole per second. I can then write what's known as the rate law by substituting in here with the actual k value that I just solved for there.